Hello. In this video, I'm going to show you how to calculate the empirical formula given mass composition or percent composition data for a compound. The two methods are very similar, with one assumption in the percent composition calculation resulting in the calculation being just like that from mass data. First, let's do the calculation for the mass composition of a compound. Let's say that we have a new compound and we analyze it and find out that a sample of compound contains 4.639 grams of carbon and 12.361 grams of oxygen. And we'd like to know what is the empirical formula. In order to determine this, we need to compare the number of atoms of carbon and oxygen. And to do that, we're first going to convert our grams into moles. So to convert grams of carbon into moles of carbon, we're going to divide by the atomic mass of carbon, 12.011 grams in 1 mole of carbon. And that gives us 0.3862 moles of carbon in this sample. Similarly, for the oxygen, we're going to calculate the number of moles, dividing by the atomic mass of oxygen, 15.999 grams in 1 mole. And that gives us 0.7728 moles of oxygen. 7728. So this tells us that our sample had this many moles of carbon and this many moles of oxygen. To turn this into a formula, we're going to divide by the smaller of these two numbers. Divide both of these molar amounts by the smaller of the two numbers. So if we divide 0.3862 by 0.3862, we get that there is 1 carbon. And for every 1 carbon, we're going to have 0.7728 divided by 0.3862. And that'll give us 2 oxygens. Let me write that down here. So for carbon, we're going to take 0.3862 moles of carbon divided by 0.3862. And even I can do this one in my head. That gives us 1 mole of carbon. And for oxygen, we have 0.7728 moles divided by 0.3862, and that equals 2 oxygens. So there are 2 oxygen atoms for every carbon atom, so our formula is CO2 for this compound. Now let's look at a similar calculation, but instead of being given actual masses like we were in this problem, we're given the percent composition. So we have a compound that consists of aluminum and oxygen, and the percent composition is 47.075% oxygen and 52.925% aluminum. Now, any sample of any size that we have of this compound is going to have this same percentage, 47% oxygen, 53% aluminum. So let's assume that we have a 100 gram sample. In that case, 47% of 100 grams would be 47.075 grams of oxygen. Similarly, 52.925% of 100 grams is 52.925 grams of aluminum. This little trick of assuming 100 grams lets us now reduce this problem to a problem like we had before, where we knew the masses of each. So we'll proceed as we did before. We'll convert the mass of oxygen into moles of oxygen, 47.075 grams of oxygen, divided by 15.999 grams of oxygen in 1 mole of oxygen, gives us 2.9424 moles of oxygen. Similarly, 52.925 grams of aluminum divided by 26.982 grams of aluminum in 1 mole of aluminum gives us 1.9615 moles of aluminum. Now, as we did above, we'll divide both of these mole numbers by the smaller one, which in this case is 1.9615. So the aluminum, 1.9615 moles of aluminum divided by 1.9615 moles equals 1. It's going to be, for every aluminum then, let's see how much oxygen there is. We have 2.9424 moles of oxygen divided by 1.9615 moles of aluminum, and that equals 1.50 oxygens. That means that there's 1.5 oxygen atom for every 1 aluminum atom. But of course we can't have half of an oxygen atom. We notice that this is a half, so we're going to multiply both of these quantities by 2. And we get our final formula, Al2O3. So this trick comes up if the molar ratio of one of the substances is a fraction. Usually it's going to be an easily recognized small number fraction. So it'll be a half or a third or 2/3, possibly a fourth or 3/4. In any case, you would just multiply both quantities by whatever the denominator of that fraction is. In this case, it's a half, so we multiply them both by 2 to clear out the denominator of the fraction to come up with the final empirical formula. This concludes this video.